Okay, this is Statistics 1, Chapter 1, Section 2. Okay, so I'm going to delve down a little more precisely in the vocab now. So data is either qualitative or quantitative, and you can look at the little prefixes. The prefixes are always the key in stats. Quality versus quantity, right? So quality, that's your categorical stuff. So basically you have distinct categories, essentially. So that'd be like colors and heights and stuff like that, you know. Not heights, colors and locations, who knows, a lot of different things, right? So basically, if it is countable, which means it's numeric data, it's either discrete or continuous, right? So your discrete data, right, is going to be countable, and it's also going to be finite, okay? Otherwise, it's continuous, okay, which means has an infinite number of values in between. So let's think about what that means, essentially. So let's say I take two numbers. We'll take the number 3 and the number 4. Are there numbers in between? Sure. We have 3.5. Okay, well, what's between there? Well, 7 is in there. Well, what's between there? 3.6. Okay, well, what's between there? 3.62. And this keeps going on and on and on and on and on, right? So this, what I'm trying to do here, if it was a continuous scale, that's not countable, because as to where the beginning is and the end is, who knows, because you can continually go in between every single number. And it's not finite, because clearly I can go forever, correct? So that's your only two choices in data, basically. So your data is either qualitative or quantitative, and if it's quantitative, it has to be one of those two types, basically. And this is important because the way you do the calculations later on are dependent on which one of these it actually is. It changes the calculation because you have continuity correction factors, essentially, and a discrete also. Okay, so let's take a look at its examples. No, that's actually correct. That's wrong on that. All right, so is it qualitative or quantitative? And if so, is it discrete or not? Or continuous if it's actual numeric data? Okay, so if I look at the statistics course and poll students determine if they are satisfied with the course, right? So I'm asking them a number, basically, or highly satisfied, moderately, something like that. And I break them out by grade, freshman, sophomore, senior. What level of data is this? We're like, well, I can assign numbers to it. So if I assign like a 5-point scale, do those numbers really mean anything? Because you have a 5-point scale or a 10-point scale, I mean, do they have any meaning relatively? Not really. So whether I use words or numbers, either way, it's a qualitative type data, right? Okay. I could also ask what movies they want to watch, what color they like, stuff like that. That's also qualitative data, right? Can't really put in order nor any numbers to it. Okay. Versus if I have to record the number of eggs that my hens lay in a month to figure out how many hens I need to get the proper number of eggs to bring to the grocery store. Well, that's number data, right? That's quantitative, right? Quantity, number. But we're going to assume the chicken can't lay half an egg, right? That's a pretty good assumption. I don't know. Maybe I'm wrong on that. So that's a discrete quantitative because it's countable and numeric, right? Versus if you manufacture something like a Pepsi, right? And you want to buy a 20-ounce Pepsi. Is it exactly 20 ounces? No. You get a bottle of soda. It's not going to be 20 ounces, right? So you got that little cap on top, right? And it's going to be filled up like this, right? So it's going to be off by, right? It might be 20.01 or 19.97. It's not going to be exactly 20 ounces because at some point, at some decimal place, it's going to be off by exactly 20 ounces. It's impossible, right? So yes, it's quantitative, but the numbers in between go forever because it's not 1 egg or 2 egg. It doesn't go from 19 ounces to 20 ounces. There's many things in between. So that's continuous quantitative data. So as far as the qualitative graphs, those are in the book, the pi, the bar, and the Pareto. We don't make those in this course, but you'll have to be able to read them. So read page 13 through 17 on those. We're only going to be making the quantitative graphs in this course in Chapter 2. The qualitative ones you just have to read. Just do a brief review of those in the book. Okay. So the sampling frame, you can think of like picture frame, right? That's the frame of all the samples that I want, right? And I have to do sampling to get stuff out of the frame, basically, right? So removing some of the picture from the frame or some of the elements from the frame, correct? So your most common methods are SRS, which is the simple random samples. You'll see this abbreviation a lot in high school AP stats and in college stats. That's where every element has an equal chance, or every member has an equal chance of being selected, right? That's ideal, but not always possible. So sometimes you'll do a systematic one where you have some kind of starting point, right? And you count over like every fifth or every seventh or every eighth, whatever the case may be. You know what I'm saying? That's a systematic routine or a system where you pick, I don't know, we'll say kth. You can use any letter you want. You like T, I guess you wouldn't use T. Any zth member, eighth member, kth member, whatever letter you want. So basically, you know, you can go every other one too. That'd still be systematic. So these are your individual methods, right? Every individual member has an equal chance, and then you're picking every fifth or every eighth person, right? That's individual. Strata and cluster, those are the group methods basically. So you need to break them into groups. So you obviously need more than one group for it to make sense. So you need at least 2 subgroups, okay? And those subgroups are called strata, which makes sense, stratified, right? There we go. Each subgroup shares some kind of characteristic, basically. And you must take from all the subgroups, okay? So this is like trick-or-treating. You go to every house, right? But you only take some candy from each house, basically, right? That's the idea. Versus cluster is another group method, just like these are the group methods, these are the individual methods. The cluster method, right? The groups are now called clusters. Same idea. I need at least 2 groups to make a sense, because one group is not multiple groups, right? But the difference here is it's not trick-or-treating. I'm taking all of the members from each cluster. So this is like going to somebody's house and taking all the candy on their porch, and then going to a couple others and taking all the candy on the porch, and then skedaddling out of the neighborhood before they catch on, right? So you went to some of the houses and took all the candy, right? And that's a cluster. So you cluster bombed their house, basically, and you took all their candy. All right, convenience sampling is when you take the easiest samples, right? Some books don't even mention this as a method, because it's not a good method. Typically, it's not a good method. Almost never is this a good method, right? And then multi-stage, which your book doesn't mention. That's when you just use multiple methods, right? Okay, which is just basically using more than one of these to accomplish the task, basically, which is fine. It doesn't have to be specifically one of these. It can be a combination of them, right? All right, so let's go through these real quick. Some different examples, right? So these are all a lot of tax ones. So the federal IRS computer selects people at Social Security number to be audited. Anybody can be selected, and the computer is doing it for you, basically, right? So since everybody has an equal chance for picking one person at a time, that's simple random sampling, or SRS, right? Okay, so the next one, the federal IRS computer selects people by Social Security number to be audited. The computer selects a person at random and selects every 3rd person. That's like every kth person, right? That's a strategy, isn't it? Systematic, right? I'm sorry, systematic, yeah. Yeah, it's a system, right? All right, so those are the individual methods. The group methods. So now the IRS selects people by Social Security number to be audited. The computer selects the country by region, and everybody in that region gets audited, right? So some regions get audited, some regions don't. That's cluster, because everybody in this region got audited, but nobody here. Everybody here got audited, but nobody there. Versus do the same thing again, but you take some from each region, right? Proportional, okay? That is stratified, right? Okay, and when you make a stratified one, the groups have some kind of characteristic. The characteristic is the region you live in, basically, if you remember the definition. Okay, all right, so individual versus group. Okay, so the federal IRS computer organizes all cities in alphabetical order by state and selects every 5th city or town. All taxpayers in this selected city or town are selected for audits. That doesn't sound like any of those. That sounds like a combination, doesn't it? Yes, it is a combination. It's more than one, right? Because you have the every 5th, right? That's the systematic, right? That's the individual method. But it became a group method because everybody in the town that was selected was taken, right? That's a cluster. So yes, it's a multi-stage. And I would call that a systematic cluster, right? And the way you word that can be a little bit different, but as long as it gets the idea. And then the worst of all, the federal IRS computer selects people by social security number to be audited. The computer selects people near the IRS building in D.C., so it's a quick commute for agents to repo their belongings. Okay, well that sounds like convenient sampling to me, which is probably the worst way of doing things, almost in every case, basically. Okay, all right. So those are all the sampling methods, but just because you did a sampling method doesn't mean it was a good sample, right? So, whoops, we got a little problem there. What's going on here? Oh, we got an extra space, that's the problem. Oh, excuse me. Okay. So just because you did some kind of, valid sampling method does not mean you're good, right? It has to be a representative sample, which means the sample actually predicts the population, right? Because a sample is only part of the population. Otherwise, you have a bias sample, which is going to under or overemphasize some characteristic of the population, basically. So that's bad, right? So if you have a problem, right, if it's not a representative sample, it's either because of sampling error or a non-sampling error. So a sampling error is natural, right? Meaning you did everything okay. It's just a natural discrepancy between the sample statistics and the true population value, right? So that means the group of people you happen to have selected didn't necessarily represent the population. So basically, a sample cannot perfectly mirror the entire population. That's what causes it. So you increase the sample size to ensure it, basically. So the more you increase the sample size, the closer it will get to the actual population. And this is quantifiable with margins of errors and other things we're going to do in later chapters. A non-sampling error, that one is the nightmare. Because if your sample is non-representative, it's because of mistakes, biases, flaws, or other things that happen during the collection process analysis. That's a problem, okay? Because it's very difficult to impossible to actually figure out what happened or predict it or quantify it or get rid of it necessarily. So causes human error, equipment defects, faulty questionnaires, misreporting, whatever the case may be. Basically improve your design, processes, and have strict controls in your sampling and processes and analysis, basically. So that's the worst one, basically. So sampling bias. A sample is collected from a population where some members are more or less likely right? To be chosen than other members, basically. Because what happens is you're de-emphasizing or re-emphasizing somebody or something in the population, and that's a problem, right? It's going to throw off your math. Okay, so let's look at some examples here. In your NCC computer system, so you use the NCC computer system to randomly select students. You measure their height, determine the average height of men and women at the college. You are not good with fractions. You continually read the measuring tape wrong on the standard end, right? So those of you who didn't grow up, working with tools and tape measures, maybe that's you. Who knows? So the problem is the non-sampling error, because it's a process error, right? Right? Your sampling looks like good. It was SRS. That was good. You might have had enough samples. Who knows? But the problem is you screwed up the process. Versus, okay, the next one, where the student used a cluster method. You select two classes at your college. You measure the heights of the students and you separate them by gender. But you find the males have an average height significantly higher than the population. Well, you did a valid method, and it looks like you did everything okay. There doesn't appear any biases here, right? So that's just a sampling error. Well, you only picked two classes. Maybe there's only 10 kids per class. So maybe it's only, 8 to 12 male students. That's too small. So yeah, you did everything correct. It just happens that your sample was too small, and it was a little off from the actual population, because the sample doesn't always match the population. So that's fine. Just get more samples, and it'll probably work itself out. Unless, in fact, there is a height difference between your students at your college versus, the rest of the population. And the last one is, okay, you do research to project determine that the most used social media platform for high school students at your school. You gather samples of questionnaires. As a senior, you only have access to older students in your common classes. Thus, few, if any, freshmen or sophomore are included. right? So the problem is it's non-sampling because your process is bad. And your process is bad because of bias. So you de-emphasized some groups and you overemphasized other groups, basically, right? You overemphasized older, you underemphasized the younger people, basically, right? Okay. So you can have non-sampling errors due to bias or not bias. That's basically what I'm trying to tell you. Okay. Either way, it's bad. You know what I'm saying? Okay. So common problems in statistics, basically. So you have misleading conclusions. This is the category. It's either detached statistic, which means detached as in like not attached. There's no actual math attached to it. Or I'm implying the math that I have actually is correlating to it, which is not necessarily the case. It actually lacks causality. Reported results is not meaning you reported something. It means you took data from somewhere but you didn't actually verify those measurements. That's bad. And small samples doesn't mean the actual sample is small. It's the number of samples is too low, basically. And there's a calculation for this for different things we're going to do later in the course. Right now, my examples are obnoxiously small, so it'll be obvious, but later on we'll calculate proper sample size, based on margin of error. Okay, then you have faulty survey questions. So you might have a loaded question, which means you have undue influence because you added something into there, which you shouldn't have done. The order of questions, you're either front-loading or back-loading it to get you to respond a certain way. Or non-response self-selected bias, which means a large number of people refuse to participate because of the fact something happened to elicit that, basically. And that's bad. And this goes to a larger category about responding or not responding and having a choice, but we're not going to get into that. For right now, we're just going to worry about this part. That people are backing out for some reason. They're going to be non-representative, basically. Because those who do respond don't represent the population, essentially. All right, bad sampling frame. There are many bad sampling frames reasonings, but I'm only going to do one, which is under coverage. So some subgroup of the population are inadequately represented or completely excluded from the samples. So misrepresented calculation, ambiguous average. So the average that was used is not indicative of what's going on, basically. It's throwing off what you actually believe or what the evidence supports. Precise numbers. You can't just scale up numbers from 100 to 1,000 and assume that when you scale it up by thousands or 10,000, it's going to be the same exact proportion as you scale it up. And then percentage manipulation. People fall for percentages all the time because without lack of context, it's easy to trick people with percentages. Misleading data, which is when you purposely, don't give all of the data or not all the information or change it, inappropriately to get a conclusion that's not okay. And confounding is when you have something that's basically, pee in the pool, basically. There's something in there you can't separate out. It's changing the outcome of the study, and that's not good, basically. It's just some third variable you weren't accounting for. And this is by no means a complete list of all possible problems or misuses in statistics, right? It's just a well-organized list of the common ones, obviously. And these are all common tactics for companies that are self-funded or self-interest studies, basically, that you have to look out for. So let's look at some examples that I made, and all of these might have multiple problems. We're going to look at the biggest problem, though, for each of these. So the first is statistical study shows that most cookie companies have switched their sweetener from corn to sugar. The result, our cookies are healthier to eat. Well, I don't see any data there, so I'm going to say that's a misleading conclusion detached statistic, right? So what I'm doing here is I'm including the category and the type, basically. So what I do in mine is I do a 1-to-1. So if there's 5 options, there's 5 questions, it's 1-to-1. If there's 10 options, there's 10 questions, it's a 1-to-1. So I'm not going to repeat them. So this happened in the 80s and the 90s. We switched from butter to margarine, then margarine to butter, and every time they told us one was healthier than the other. Same thing with eggs. First they said eggs was healthy, and they said eggs are not healthy, and then they went back and forth, right? But you need context and data to back that up. So a statistical study finds that at a fire, if you increase firemen, or when there was increased firemen, there was more property damage. That must be the firemen's fault. No. That's actually an implied connection. It's a misleading conclusion. Just because you have data does not mean there's causality, basically. So a research study looks to figure out if large consumption of alcohol will reduce your life expectancy, your natural life expectancy. But the problem is some people are dying because of car accidents or just accidents in general, auto accidents, right? So that's something I can't take out of the study, right? It's like the pee in the pool. Can't take it out. It's messing up the study now, right? The chemistry is all wrong. So that's a confounding problem, right? It's not really sure how to get rid of it, and it's screwing up the results, basically. It's like a third variable we can't account for, basically. Okay, so department head asks one student about a teacher, and they make an evaluation. Well, I'm pretty sure one student is not enough. You need better than that, correct? So that's definitely a small sample. And again, later chapters will calculate proper sample size. Right now, we're just doing obnoxious ones. So a study asks weightlifters to report their height and max weight they can power lift. Well, okay, are they going to be truthful about that? Maybe, maybe not. You didn't verify that the actual data, so that's a reported results problem, right? Reported results is you got data, but you didn't verify those measurements. Basically, that's a problem. Okay, so the study asks, since Bernie Madoff scandal has happened, right? So remember, this is the biggest, you can Google this if you want, that's the biggest Ponzi scheme of all time, at least at the point I'm making this video, I believe. If you believe billionaires are evil, well, you should be adding things to it to sway somebody's opinion. You just ask the question, pretty dry. So that's a faulty survey because I loaded the question, basically. Okay, versus this one, essentially asks if they believe factories cause more pollution than individual people. Well, wait a minute. The wording of that is weird. It's still a faulty survey, but shouldn't I ask pollution because of factories or individuals? No, I'm just putting one in front of the other, aren't I? So I'm basically front-loading the question so that I get a response that the factories cause more, aren't I? So that's a faulty survey because I played with the order of the question to front-load it, basically. Okay. All right, next page, look at some others. So, online hotel survey says that 1% of visitors claimed they had clean room, and after work they cleaned their rooms. Now they report 100%. Well, 100% of what? And then this is 1% of how many? We have no idea. And if you're at 1%, you only get 100% improvement. That doesn't mean you're 100% now. That only means from what you were before, which is to what number that was before, who knows. It's probably not very good. So I'm misrepresenting my calculation with percentage manipulation. I'm trying to trick you, basically, with you not knowing how percents work and the fact I'm not giving you the context of the percent, basically. Okay? All right, next one. You work in a political campaign. You create your own polls. You go door to door asking people who they support. You wear a pin with the candidate that you support. Most people slam the door in your face. Well, that's not good. Now it's not representative because you have people who are not giving you any data, right? So they're self-selecting and they're non-responding, right? Either one of those is the same thing, depending on which book you pick up. It's like elevator versus lift. So now the people who are responding are not representative of the population because you left some people out. You know what I'm saying? As to why they're left out, who knows? You know what I'm saying? You might say bad sampling frame, but the problem is we don't know exactly why, so it's kind of hard to tell. Why, what the groups would be necessarily, versus J, right? The student body, you survey the student body to see what they want the school dance team to be. You don't ask the freshman class since they're not in the building. Well, that would be a bad sampling frame because you know what the under coverage is. You know that it's people that are freshmen, basically. You don't know the other one necessarily, other than the fact they just didn't like your pin, maybe. Who knows? Or maybe they just didn't want to answer because they just don't like people showing up at their door. I know mine and where I live, and you cannot go to people's doors and just start asking them questions. They're not going to be very happy with that. Okay. A student body at your college is 10,000 students. You sample 1,000 of them, and you get 371. So you just scale it up. You can't do that. There's a lot of reasons why you can't do that. That's using precise numbers. You're misrepresenting your calculation. You can't do that. You can't just ask 10 people and scale it up to 10,000. It doesn't work that way. Okay. It proportionally changes, which we'll talk about later on. Okay. Let's say you are in Sunapee, New Hampshire, a real place like Sunapee, and you want to raise taxes on residents, and you take the average income of people, and Oprah Winfrey lives there, at least she did at one point, and she's a billionaire, so you look at their average, you're like, wow, people are making a lot of money. Well, here's the problem. It's a small town, and one billionaire is going to offset the average in the town, right? So that is misrepresented calculation because it's an ambiguous average, basically, which is why they typically use median income and median household, and household cost and stuff like that, or house prices, instead of average. The same thing happened in Boston. They used to, a couple of years ago, they were saying, the average Bostonian makes $275,000 a year. Well, yes, the average might, but the median did not. The median was far less than that. The problem was the billionaires in New England almost primarily live in Boston, so that threw off the average, obviously, so it's the ambiguous average as a result. And the last one shows the house prices greatly increased from 1998 to 1999. I've seen graphs like this before in the news about house prices and other things over the years. And what they tend to do is they take this little scale here on the Y and they just zoom in a lot. That's kind of dishonest. It didn't really change all that much. So that's just a misleading data, basically. Okay? All right, that's the end of section 2.